Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to see the topic on capacitance of coaxial cable and also energy density in a capacitor. So, a coaxial cable consists of two conductors separated by a dielectric material. And consider the inner conductor is having the radius A and the outer conductor is having the radius B. Both the conductors sharing the same axis so that it is a coaxial cable. And let the dielectric medium having the permittivity epsilon, and the length of the coaxial cable is taken as L. And the inner conductor carries a charge density rho L coulombs per meter on its surface, and definitely there will be equal and opposite charge density minus rho L coulomb per meter is exist on its outer surface. So to calculate capacitance, we need charge and the potential difference. So the charge Q can be obtained by multiplying the charge density and the length of the coaxial cable. So Q is given by rho L into L. And assuming cylindrical coordinate system, the electric field is radial from inner conductor to outer conductor for infinite line charge, and we know the formula to calculate the electric field of a coaxial cable is equal to rho L by 2 pi epsilon r into AR vector. So now we need to calculate the potential difference, and the potential difference is nothing but the work done in moving a unit charge against the electric field, that is moving the charge from R is equal to B to R is equal to A. So the potential difference V can be given as minus negative integral of the radius value R is equal to B to R is equal to A rho L 2 pi epsilon R AR, and the DL is given as AR DR. So we know that AR dot AR is equal to 1. So, and the integration is only for dr, 1 by r into dr. So we know that and the remaining terms are constants, that is rho L by 2 pi epsilon are constant. We have the integral term integral of r is equal to b to a 1 by r into dr. So we know that 1 by r into dr, the integration is ln of r, natural logarithm of r. By substituting the limits, the upper limit a and lower limit b, we get rho L 2 pi epsilon logarithmic of a to b. Here we have negative sign for the potential difference. In order to change this negative sign, we can change the expression as v is equal to rho L divided by 2 pi epsilon natural logarithmic of b to a. So here the numerator and denominator value changed so that the negative sign become positive sign in volts. So the capacitance is finally found out by substituting the values of Q and V. Q is equal to rho L L, V is rho L by 2 pi epsilon ln of B by A. Here rho L is cancelled because it is in both numerator and denominator. So the final expression for the capacitance of a coaxial cable C is equal to 2 pi L divided by ln of B by A in farads. So in this way the capacitance of a coaxial cable is calculated. Next we come to the next topic, a very important one, the energy and energy density of a capacitor. So the energy stored in a capacitor is nothing but electrical potential energy, and it is always related with charge Q and the potential difference V on the capacitor. And the energy density is nothing but it is a measure of the amount of energy stored in a given volume of the capacitor. So this energy density is an important parameter when designing the capacitor for various applications, because the selection of capacitor can influence the size and efficiency of the device. So now, in order to find out the energy stored in a capacitor, for an example, we have taken a parallel plate capacitor having the separation between the parallel plates D, and the area of the parallel plate is A, and a battery is connected with voltage V. So in this case, for finding the energy stored in electric field, the expression for WE is 1 by 2 integral over the entire volume d dot E dV. So here d is nothing but displacement density vector, E is the electric field. So the electric field is given by for parallel plates, it is E is equal to potential difference V divided by separation between the plates D multiplied by normal vector, unit normal vector, because in this case the electric field is perpendicular to the parallel plate. So here it is given with normal vector. So, and also we know that displacement density vector D is epsilon into E vector. So by substituting in energy density expression 1 by 2 volume integral of D is replaced by epsilon E dot E dV. We know that E dot E vector is equal to modulus of E square, and so 1 by 2 epsilon, this E is the voltage divided by the potential difference divided by the distance of separation between the plates. It is substituted in the energy density expression. So we get 1 by 2 epsilon V squared by D squared integral of dV over the volume. So integral of dV is nothing but multiplying the area of the plate into distance of separation d. So by substituting all the values, we get the energy density of a capacitor is 1 by 2 epsilon V squared AD by D squared. So dd get cancelled, and this epsilon A by D is nothing but the capacitance C. So replacing epsilon A by D by C, the capacitance value, energy density stored in a capacitor is given by the expression WE is equal to 1 by 2 CV square joules. And energy density is nothing but the energy in per unit volume when the volume tends to 0. So WE can be given as 1 by 2 epsilon integral over the volume E squared into dV, and this volume tends to 0, so we remove the integral. So WE energy density is equal to 1 by 2 epsilon E square joules per meter cube. So here we have taken the volume, so it is meter cube, and this D vector we can replace it as epsilon E. So we can modify the previous expression. WE can be 1 by 2 modulus of D squared by epsilon, or 1 by 2 modulus of D vector modulus of E vector joules per meter cube. So this is about energy density expression. And there are various factors affecting the energy density of a capacitor. One is the dielectric material property. We know that it is permittivity, and also the dielectric constant. The material with higher dielectric constant can store more energy per unit volume. So higher dielectric constant material will store higher energy densities. And the next parameter influencing the energy density of a capacitor is its geometry and design. So a larger surface area of the plate and also smaller separation between them will result higher capacitance. So if the capacitance is higher, naturally the energy density will also be higher. And the third parameter is the operating voltage. So the operating voltage will also influence the energy density of a capacitor. So if we have maximum voltage, the maximum amount of energy can the capacitor can store, so it causes higher density. So even though higher voltage, by applying higher voltage can have higher density, a capacitor cannot withstand maximum voltage rating, because if it is beyond the maximum threshold voltage level, the dielectric may break down and the capacitor may fail. So these are the various factors affecting the energy density of a capacitor. And next applications part, the applications of capacitor energy, it can be useful for various applications. For example, the capacitor energy can be useful for audio equipment, uninterruptible power supplies, camera flashes, pulse loads such as magnetic coils, and also the lasers use the energy stored in the capacitors. Assessment: the capacitance of a coaxial cable, define energy density, how to find energy stored in a capacitor. Thank you.